Hey everybody, this video is going to go through probability. It's a lot of review from geometry, and we're going to kind of skip around on these notes, just kind of hit some of the bigger concepts for you guys. So you did statistics in the last video, now probability, and then you guys are going to take a quiz over everything we've covered these 2 weeks. So first thing we're going to talk about is outcome. This is the possible result of a possible result of an event or experiment, but we're going to go with event because we're talking about probability. Sample space is set of all possible outcomes. So it comes from above. All the possible outcomes. The sample space of rolling a 6-sided number cube is we list it. So a sample space is a list, and it's listing all the possible sides we can get from a number cube, which is 1 through 6. And we use these little curly brackets, look like this, when we talk about a sample space. Probability is the likelihood an event occurs. And we can do it as a fraction, decimal, or percent. And then that's it. Well, symbol, you do like probability of A, however you want to look at it. So we're going to look at a couple of examples. Rolling a 2 on a 6-sided number cube. So how many 2s are there on a 6-sided number cube? There's only 1 2. And how many total sides are there? There's 6. So it's 1 out of 6. Rolling an even number on a 6-sided number cube. So how many even numbers are there? There's 3 of them. We have 2, 4, and 6. Out of how many total sides? 6. And we always reduce, which is 1/2. All right, let's go to the next. A tree diagram. We did one of these last year, I believe. A tree diagram is a way to find the total possible number of outcomes of more than one event. So, for example, Miguel is going to select an outfit from 2 different t-shirts. He's got a tan one and a red one. 2 different pairs of shorts, gray and khaki, and 3 pairs of socks, black, navy, and white. Draw a tree diagram to list it all. So we could have a tan or red shirt. Okay, but now if I pick a tan shirt, I can now choose gray or khaki pants. Or if I chose the red shirt, I could also have gray or khaki pants. So no matter what shirt I choose, I now have 2 options of shorts. Same thing happens here. I could have a tan shirt, gray shorts, and I have 3 options of socks: black, navy, or white. Same thing here. I could have black, navy, or white. So for all of these, I could have any scenario. So I could have a red shirt, gray pants, and white socks. I could have a tan shirt, khaki pants, and a black pair of socks. So this is showing all the different types of outcomes, and the total number of outcomes is how many I have, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 outcomes between this situation here. The probability that Miguel will select a tan shirt, gray shorts, and black socks. Well, how many combinations of this are there? Tan, gray, and black. There's only 1 combination like that. So it's 1 out of our total, which is 12. Probability that he will select a red shirt and gray shorts. So how many possibilities if I choose a red shirt with gray pants? I could have 3 different kinds because it doesn't talk about socks. I have 3 different pairs of socks I could wear. So this is 3 out of 12, which we reduce it to gives us 1 out of 4. And then what is the probability that he will select an outfit with khaki shorts? Well, how many khaki short options are there? Well, here's khaki. I could have khaki with my red shirt and 3 different pairs of socks here. And I can have khaki here with a tan shirt and 3 different pairs of socks. So 3 plus 3 gives us 6. It's 6 out of 12, which reduces to 1/2. Okay, next thing is fundamental counting principle. Another way to find the total number of outcomes, especially when there are a large number of them, you just multiply. That's all this is. So a deli is doing an inventory of their sandwich ingredients. They have 6 different types of bread, 8 types of meat, and 4 types of cheese. We multiply that together and we get 192 possible outcomes. Sorry, you can't see that. We could have done the same thing up here. We had 2 shirts, 2 shorts, and 3 pairs of socks. 2 times 2 is 4, times 3 is 12. So it works no matter how little or how many numbers you have. This is just called the counting principle. All right. Okay, so now we have compound events. These are a combination of 2 or more events. We use and or. We definitely talked about this in geometry last year. So if we're using or, it's U for union. And because of the amount of notes, I'm going to just leave this on here. You can pause it and copy them down. But they're mutually exclusive events. They are events with no common outcome. If they are overlapping, they do have a common outcome. So you could see it either way. If they are mutually exclusive, and what this means is that if I have mutually exclusive means I have set A and set B, and there's no overlapping. Overlapping would be like this. So if you're comparing, let's see, an apple to a die, they have nothing in common. So they would be mutually exclusive. If I'm comparing Biggie to Tupac, they're both rappers. There's stuff that goes along with both of them. So there's overlapping between those two things that we are comparing. So mutually exclusive, you just add them together. The probabilities, add them together. If they are overlapping, you add the 2 probabilities together and subtract the overlapping, because what's happened now is we've counted this twice. Because if I count all of A and then all of B, I've counted this twice and I only want to count it once. So those are your formulas. And then if it's an intersection, in, intersection, and, we have independent and dependent events. So here are your formulas. You just multiply them together, and that'll give you independent. If they're dependent, you're using conditional probability. So independent are events that do not affect each other. Dependent are events that affect one another. So if I flip a coin and roll a die, they don't affect one another. If I draw a card and don't replace it, instead of 52 cards, I now only have 51. So it's going to affect my probability. So again, you can pause these and copy them. And now, doing some examples with this. So you randomly choose a card from a standard deck of 52 cards. Find the probability that you choose a queen or an ace. So remember, if we're looking at the formula for or, all we do is we add. So or, add. So the probability of choosing a queen, how many queens are in a deck of 52 cards? There's 4 of them. out of 52. And how many aces are in a deck of cards? 4. And just like our formula, we add, and we get 8 out of 52. And then you'll reduce it, and that'll give you 0.154. And remember to get it into percent form. All you do is move this decimal 2 times, and you get 15.4%. Probability that you choose a king or a club. So how many total kings are in a deck of cards? There are 4. How many total clubs are there? Well, there's 13. Is there any overlapping? And yes, there is a club king. So we need to subtract that club king from here because right now it's counted under kings and clubs. So we have to take that 1 away. And when we do that, we get 16 out of 52, which gives us 0.308. Move the decimal, and you get 30.8%. All right, let's go on to number 5. A coin is tossed and a 6-sided roll is rolled. What is the probability that the coin shows head and the die shows a 5? These are independent events because me flipping a coin and me rolling a die don't affect one another. So if we are doing independent events, all you do is multiply. So the probability that the coin shows up on a head, how many heads are there? 1 out of 2. And the die shows a 5. Well, how many 5s are there on a 6-sided die? 1 out of 6. Multiply, you get 1/12, or 0.083, which when we move the decimal gives us 8.3%. What is the probability that the coin shows tails and the die shows an odd number? Again, they're independent, so all you do is multiply. So in this case, it's 1 out of 2 times 1 out of 2 gives us 1/4. Half of the coin has a tail, and half of the die has odd number. You could also have done 3 out of 6, which is the same thing as 1/2. Either way. Now we're going to get into dependent events. An aquarium contains 6 male goldfish and 4 female goldfish. You randomly choose one fish from the tank without replacing. So that means I take a fish out and I don't put it back before I pick the next one, which means it's going to affect my outcome of the next fish. What is the probability that both fish are male? So each fish is a probability. It's an event. So we have 2 fish, and we need to find the probabilities of those happening. So the first time, what's the probability? It's male, 6 out of 10. But I took that male fish away. So how many male fish are left? 5. And again, I took that fish away. So how many total fish are left? 9. So each time you're going to subtract, and this gives you 1/3 or 33.3%. And then to determine if they are independent or dependent, if I multiply these and it gives me this answer, then it's independent. If not, then it's not. So when we multiply 0.5 times 0.7, you get 0.35, which does equal this. So yes, they are independent. Sorry, you can't see that. Here, when I multiply 0.3 times 0.2, we get 0.06, which is not the same as this. So no, they are not independent. All right, and then we've got a couple more concepts to talk about.